Going.
Okay, so for your homework solution, I thought we'd make a video, and where Dean Walton, a science librarian, has made this cool thing, so we're going to test it out. It's a toy. So this is problem 82 in chapter 4. This was the third problem on your homework, and arrow on a hill. So I wanted to show a solution where you could use tilted axes. It works absolutely fine if you don't tilt your axes. If X and Y are pointing kind of like normal, horizontal and straight up, that works. This one's going to be tilted. So whenever you're solving a problem, if you don't know how to start it, first you got to choose your model. So be asking questions like, do we need to worry about air resistance, the shape of the arrow, things like that. We're going to be making approximations mostly. So in that model, the arrow is a particle. Following parabolic motion. Parabolic motion. We'll ignore air resistance. And what else? That's good. Okay, so now what's our scenario? We got a hill, and when I'm making my diagram, always be thinking, get rid of the numbers as soon as you can. Okay, that's going to help you, I swear. It's hard, it's not intuitive. So we're going to call this theta. And there's an archer up here, and the arrow follows this kind of motion. And I'm making a dotted line that's kind of a mix between a motion diagram and just a dotted line. But the point is, it's going to follow this trajectory, and it has this initial velocity, v0. Now, we know that the horizontal angle that this makes, this is a different angle, we'll call this phi. Okay, and now what we're going to do is choose some different axes. So maybe I'll use blue for my axes. And here we're going to choose an axis where it starts off at x equals 0 and some y value. So this is going to be our I hat direction and our j hat direction. You could choose different x, y axes, that's fine. We're going to try our tilted axes. Okay, so now say we still don't know how to solve this, but we're choosing parabolic projectile motion. And this is in chapter 4, so the model is going to be in chapter 4, which is all about projectile motion. It's probably not angular motion here. It's probably not relative motion. Actually, projectile motion is an example of relative motion. The point is, we're going to use these kinematic equations with acceleration due to gravity. So here's our x direction. It's going to be x0 plus the original velocity in the x direction plus whatever acceleration there might be in the x direction. We could use the derivative of that, so the velocity as a function of time could equal the original x component of the velocity plus whatever acceleration times time in the x direction. Likewise with y. So again, let's just pretend we have no idea how to solve this. We just have some loose intuition that's going to involve these equations, because all projectile motion problems typically involve these equations. And our accelerations are going to have something to do with g, right? So that's all we know right now. We haven't thought this out. Okay, so now what's the other thing I need to do? Gravity is at play. So I need to draw my gravity vector. There. Regardless of my tilted axes, I know that g points to the floor, right? Okay, so now we can start solving. We know these things. I guess there's those other weird kinematic equations. Let's go with these for now. Now, the next step in that problem solving thing is to kind of write down a table of what we know and what we don't know. Okay, so we know that this angle, theta, is 15 degrees. and we know that phi is 20 degrees. We know that the original velocity, the magnitude, is 50 meters per second, right? Okay, and now we've chosen axes. We can now write tables in the x direction. The original position we're defining to be 0, right? We've chosen coordinates where it starts off at 0. X1, the final location, we don't know, but that's kind of what we're looking for, right? It's asking how far down the hill has this gone. So that's what we want. That's good. We should write that down. Okay, what about our original x component of our velocity? Well, okay, so now because of our axes, we're going to have to think about decomposing this vector, v, into two vectors. So I'm going to move this guy a little bit. Now we'll keep him there. Okay, so this is the x component of that original velocity vector, and it's pointing down the hill because we've chosen axes that way. And then at a right angle, we've got the y component coming up. And if you do your trig, that inner angle right here is going to be theta plus phi, right? We have the tilted hill, so it has to do with our rotated coordinate system. So that's theta right there, and then we've got phi right here. And if this isn't obvious to you, you have to go back, work out the trig. This is going to be cosine theta plus phi. And again, I'm not just writing in 35 degrees. I'm using my signs now. Our final velocity in the x direction is going to be changing because now there's a component of the acceleration due to gravity in the x direction. So it's not going to be this. We don't know what it is, but who cares? It's not asking, problem's not asking for that. We don't really care about the velocity when it hits. If you were the archer and there's some person trying to attack you, you'd probably care a little bit, but we don't for this problem. Okay, now the acceleration in the x direction. Well, again, we can choose our tilted axes. I can draw them up here. So y is pointing directly away from the hill. And my i-hat direction is pointing directly down the hill. And so now there's a component of g that's pointing in this x direction. That's a sub x. And there's a component of g that's pointing in the y direction. And if I do my trig, then again, g is pointing straight down. You can use all your geometry and trig to show that this angle is equal to this angle. Okay, so ax is going to be just g sine theta. Does this make sense? Well, if theta were really small, there should be no x component, and sine of theta, sine of 0 would be 0. Okay, that seems about right. Now, if I plug in numbers for these, you'll get v naught x, let's see, is 40.96 meters per second. v1x, we don't know. A sub x is equal to 2.54 meters per second squared. Okay, so now let's do the y direction. Okay, where does it start off at? So here, now I know the archer is 1.75 meters tall. It's about 5'9". But I'm not going to worry too much about whether they're leaning or not. I'm just going to say that they're starting off at 1.75 meters. Y final? What's y final? Do we know? Well, we want to know how far this arrow goes when it hits the ground. The way we've drawn our axes, the ground is at 0. So we want to know how far the arrow goes in the x direction when y1 is 0. Okay, now what's the original y component to its velocity? well, it's just v naught times the sine of theta plus phi. And if you plug in your numbers, that's 28.68. Again, the final y component to the velocity, we don't know. And here again, we don't really care. You can go ahead and write it down. It's not going to harm you, but it's extra work. Okay, a sub y now. Well, whenever we're doing these things, x and y are usually related by a sine and a cosine, so it's probably going to be something like g sine of theta. So this will be g cosine theta, and we want it to point in the negative direction. And if you do this bit up here, you'll get the same answer, negative 9.46. And again, I'm thinking about this as I go. 9.46 is less than 9.8 meters per second squared. So that makes sense since we're kind of like tilting our thing. Okay, so now we're looking at these things and maybe we still haven't formed a strategy. So now suppose, okay, I'm looking at what I know, I'm looking at what I don't know. I want this thing. If I use that other kinematic equation and I knew what the final velocity was, I could figure out that thing, but I don't know what that is. So can I use one of these over here? This is x sub 1, that's x naught. I know v naught x, I know ax, but I don't know time. Okay, so I need to figure out time. How do I figure out time? So if I go over here, which one of these equations, I got these knowns, which one of these equations has the least amount of unknowns? It's this one. Okay, so what is this? We think of this equation, but then we think in words, what is this telling us? This could tell us the flight time if we could solve for t. So we're going to use this equation with this information. Plus v naught y. Oops. Times time. Oops, that's times time. Plus 1/2 ay t squared. Now if I subtract y1 from both sides, then I get 0 is equal to y naught minus y1 plus v naught y times time plus 1/2 ay, that's squared. Okay, and now I want to solve for t. This is just a quadratic equation. So solve for t. T is equal to negative b, which is v naught y, plus or minus the square root of b squared, that's v naught y squared, minus 4ac. A in the quadratic equation here is 1/2 ay. C squared is y naught minus y1. Now I already know y naught is 0. It's okay to plug in zeros in your equation. All other numbers leave out of them, but 0 here. So this just leaves, or y1 is 0, so it's just y naught. No, y naught is 0. y1 is 1.75. Okay. All over, so 2a, it's over 2a there. So 2 times 1/2 ay. Okay. So you do this, you plug in numbers, and in the end you get the two answers for t. One is negative, so it's like negative 0.06 and 6.12 seconds. Okay, so now we're thinking, okay, we got two answers for time. Why do we have two? Which one's right? Which one do I care about? Well, negative time. Over here, I've assumed that time t equals 0 is when the thing launches. So negative time would be somewhere like back here. So what this means is if the arrow had started off at the ground, that's when it would have started off at the ground. Remember, we've solved for whenever y equals 0. And it could have started off at the ground then. So this is the one we want. Okay. So now we know the flight time. This is the flight time. Okay, so now we put this into x1. 6 seconds sounds like a long time. If your enemy was running up the hill at you, charging, and you're defending, you want to launch, but they got plenty of time to run. So you might want to wait till you can see the whites of their eyes before you fire. Okay, so now we're going to plug this into the x direction. So x1 is equal to x naught, which is 0. I can go ahead and plug that in, plus v naught x, which is 40.96, times 6.12 seconds, plus my acceleration in the x direction, which is non-zero at this point, again, because we're choosing an x that's kind of pointing downhill a little bit. So this is plus 1/2 g sine theta times 6.12 seconds squared. Okay, so you plug this in, plug in all the numbers, make sure the units work out, and you get 298 meters. And there's your answer. But now, if I were to be a stickler for my units, nothing in the problem gives me more than 2 digits. So I might express this as 300 meters instead. 300 meters is the range. And there's my answer. Well, there's an answer. Next step in that problem solving, I'm not done yet. Does this answer make sense? So 300 meters, let's see, that's 3 football fields. Does that make sense? That's a long ways. That's like 1/3 of a kilometer. Sounds like a long ways for an arrow. On the other hand, it was moving pretty quick, 15 meters a second. If you've ever done track, it's like half a football field in a second. So that arrow's really moving, plus it's pointed downhill. So I think that kind of makes sense. 300 meters sounds about right. So you should always kind of go through that logic a little bit. Okay, there we go.